if you look at it for quite some time, it has mainly been a domain for physicists and for mathematicians, working with the theory of quantum and working with the physical aspects of handling qubits and manipulating qubits. But of course, when they succeed, and I say when because we have quantum computers today, but they're still very limited. But of course, at one point, we would have to have the software stack on top of that. And this is where I think our community have to gather together to find and try to find out what this is about. And I couldn't find anyone better than Robert Wille to do this. Robert is a full and distinguished professor at the Technical University of Munich. He's also the chief scientific officer at the Software Competence Center in Hagenbach in Austria. That's a technology transfer company with 100 employees. He received his diploma and master degree from University of Bremen in 2006 and 9, and he has been involved in a lot of different things. So I think one of the reasons he is interesting to present here is that, I mean, he is a computer scientist, but he's working with the design of circuits and systems in both conventional technologies, but also in emerging technologies, and quantum is one of the emerging technologies. Robert has also worked with microfluidics that some of you saw yesterday and so on. But I think quantum is something that is for all of us. It's not just the work stream on cyber-physical system, but it's something that we all need to understand to the extent that you can understand. So with these words, Robert, the stage is yours. I know you would have liked to be here physically, but that was not possible, and we are happy that we actually could get you out of what you are doing and giving us this presentation.
Yep, perfect, Jan. And apologies again that I cannot be there physically, but yeah, it's great to be here. And thanks for the invitation. And Jan, you actually gave a great introduction. What is actually kind of my mission for a couple of years? Actually, I work in quantum computing for more than 10, 15 years. And Jan, exactly as you said, it's a topic or domain which is heavily dominated by physicists, which is absolutely fine. We need those expertise in order to build quantum computers, but more and more, and indeed we need also the software stack. We need also other expertises to build in. And this is actually also the case I want to make in my talk here. So I'm just to make that clear, I'm a design automation expert by training and computer scientist by training, and that's also how I see this whole domain of quantum computing. And you know, I think I directly jump into my talk because it's very much in line with what Jan said. In order to make my case, why we also need design automation expertise, software expertise, and also trying to make the case in order to make a contribution, in order to help developing the software stack for quantum computing. You don't need you don't need to be a quantum physicist. Actually, we can use a lot of abstractions which still help to make an impact here. So I jump right into it. So you know, quantum computing is a thing which came up. I don't want to actually talk too much about what is quantum computing and the applications, why it's important. It has some sort of momentum. There are a couple of so-called killer applications which seem to be very promising, or applications where people believe, and where first kind of case studies have been made which showcase that quantum computers can solve certain problems much faster and much more efficient than in the conventional realm. I don't want to dive too much into that. Jan already mentioned that. It's a little bit more, it seems at the moment that it is more a question of when does this really come? So we have quantum computers, we have already applications running on them. The question just when we get quantum advanced, or sometimes it's called quantum supremacy. So when do these quantum computers get into some sort of maturity that we really have real world instances that can be solved with that? That's more like a matter of questions. For some problems, you probably have heard about this integer factoring thing. This seems to be very far away. Other problems like solving optimization problems, doing simulations seem to be a little bit more in the future. However, this is not what I want to focus on here. There are probably other experts and other people who can talk better about that. Here I'm just saying sort of it seems to be at the moment that in the past years some impressive improvements have been done also by big players such as IBM, Google, Microsoft, and so on and so forth, which work on quantum computers and which try to really make get this kind of quantum advantage, finding applications where quantum computers can make a difference here. But I sort of take this as a motivation, but I don't want to dive too much into it. I want to focus much more on the current development and what we as design automation experts or software developer can do here. And for this, I would like to make a brief comparison and a couple of synergies. And for this, let me quickly review. This is sort of like how quantum computers look like at the moment. They fill entire rooms, but we also can see interesting progress. This is just, it's a little bit older statistics, but it's a roadmap by IBM showcasing what kind of qubit development they are expecting, or they had in the past and they're expecting in the near future. And now I have to say qubits, or just counting the number of qubits, might not be ideal. It's actually a bad metric in order to summarize computing development, but nevertheless, it shows a little bit that there's a very upward trend forwards. And then also IBM is all about metrics. They also have another metric called quantum volume. And also here you can question how accurate is this metric, but this is another metric showcasing a little bit how powerful quantum computers are. And if you check out recent IBM quantum computers, you can see no matter what this quantum volume really means, but there's some sort of an exponential growth in the development of new machines. And I'm not saying this is another Moore's law for quantum computing, and there are some reasonable concerns whether or not this development will go on. But I think it's fair to say that quantum computing hardware is evolving, and it has some sort of momentum right now. Whether or not it's going to be another Moore's law for quantum computing, I wouldn't claim that here, but there's definitely some progress. And this is what I find particularly interesting. This is very similar to what we have seen in conventional computers. Also, conventional computers first consumed entire rooms. And then, as you know, with Moore's law and with this development of it, we have seen a tremendous improvements in the semiconductor industry, in the way how we're developing conventional computers. And I'm not saying that we have exactly the same thing in quantum computing, but there is a certain analogy which is interesting. And this also brings me to the point that, after all, conventional computers occupied all aspects of our daily life because of this development in the semiconductor industry, but also because we had design automation tools. Because without the design automation, you wouldn't be able to design a smartphone composed of billions of components. So at some point, you had electrical engineers working on conventional computers, and then at some point you recognized you need assembly languages, programming languages, design automation tools, software, and actually design automation in general. And this led to several very powerful tools like subsolvers, like dedicated decision strategies, A-star, so literally everything the design automation community has developed over the past decades. And I think this is one of the main reasons why we have these powerful conventional computers today. Also, in addition to the fact that we were able to incorporate all those methods and tools into very dedicated and complex design flows and compilation flows. And you can really see that if you look at big players like I said, like IBM, more like Infineon or so, there is not a single person who designs a new smartphone or a new computing device, but you have lots of groups of persons and entire groups that just focusing, for example, on testing something or on designing something, on getting something synthesized and stuff like that. And this really shows how dedicated and how powerful design of conventional computing became. And my point is a little bit that if we check out the same development for quantum computing, then we have to conclude that for quantum computing, we have first tools, we have first IDEs that allow the design for quantum computing, but they are by far not as powerful as the design tools we take for granted in the conventional realm. And the same also holds when we come to design flows. Of course, we know roughly how to design a quantum circuit, but again, I wouldn't say those are as powerful as the design flows we have for conventional realms. So I think there's a huge need, and this is also what Jan mentioned in the introduction, that we right now can really see more and more a demand for which, in addition to the expertise from physics, we also need more and more expertise from computer scientists, design automation engineers, from people who develop methods and develop methodologies to make actually, to really design and realize quantum applications on a very high level. Because if we don't do that, we may end up in a situation where we have quantum computers, but no efficient methods to use or to design them. And this is sort of one of the main messages I want to give here, that sort of like it is right now, it is really the time to get broader disciplines, broader spectra of expertise involved in this domain, because quantum physicists, they're important in order to build the computers, but in order to use them, in order to design algorithms for them, we really need also the other expertise. And then you may ask, okay, but what's the big deal? Why can't we simply copy, paste, or reuse the existing design automation methods we have for conventional circuits and systems, and why can't we simply reuse them for quantum computing? And obviously there are a couple of obstacles and challenges, and let me just illustrate a couple of them. I don't want to dive too much in detail, but to give you an idea, what are actually the kind of change in the mindsets we need in order to develop design tools for quantum computing. So first, and it's probably not what you would have expected first, but I think it's a great example. Usually when you talk about quantum computing, the first thing you tell us, okay, compared to conventional realm, to the conventional realm, you not only have zeros and ones, but everything in between. And this is true, and this is a big challenge. But let me start with another kind of paradigm first, which is very similar to what we've seen in the conventional realm. In the conventional realm, we have programming languages, and we use C++, or Python, or Java, or VHDL, whatever design language we want to use. And here we inherently use something like multiplication. But in quantum computing, we have really the problem that certain operations are simply not allowed, because everything in quantum computing needs to be reversible. And multiplication simply isn't. As an example, reversal means you can determine the output from an input assignment, but also the other way around. So in this example here, it's no problem to determine the product of two values, 4 and 5, that is 20. So this direction is no problem, as in the conventional realm, but the other direction is not possible, because if I give you 20 as an output and I want to ask you, okay, what is the inverse of that? What's the reversible output of that from the multiplication? You can come up either with 4 and 5 again, or with 2 and 10. So that's the first. It's not the most important challenge, but it's a chain in the way how we program or how we think about algorithms in quantum computing, and that you simply cannot have a multiplication like that, or an assignment operation in general. What you have to do is you have to add some sort of an extra variable in many cases, and then you're only allowed to have so-called assignment of reversible assignment operation. You cannot simply say C equal A times B. You have to incorporate it with an assignment operation like this increase operation. Then you can calculate in both directions. And this is a huge challenge which needs to be considered. Again, not the biggest one, but simply spoken, we still use C and Python and all these kind of programming languages in order to control and in order to design and to trigger algorithms, but the algorithm itself, the quantum algorithm itself, cannot utilize C equal A times B. It always has to be incorporated into a reversible fashion, such as sketched here. Besides that, of course, now I come with the 0 and 1 thing in at the same time. Of course, in quantum computing, we're dealing with zeros, with ones, but also with everything in between. We have this super precision, and of course, this has to be handled somehow, which is a challenge on its own. Also, there are lots of quantum operations which we heavily rely on in the domain, which are not that intuitive. And I think this is one of the biggest challenges as well. So I'm not sure you in the audience, I'm not sure who of you is familiar with something called an Hadamard operation or something called a Toffoli operation. Those are actually not very complex operations, but those are operations we heavily use in quantum computing. And here I see a big challenge. Although these operations are not that complex, we as typical human beings with a school education, with a university education, we are not familiar with that. And I think that's a big challenge, because when we built conventional computers in the past, when we built processors, for example, in the past, we still realized something like addition or multiplication or subtractions. So although we did it with, you know, with zeros and ones and with elementary gates and stuff like that, we still used operations we all learned in school and we are very familiar with. When we work on quantum computing, suddenly we have to deal with the aforementioned Hadamard operations or Toffoli operations, which we simply haven't learned in school. That means on top of understanding that quantum computing has different gates and different functionalities, different paradigms, on top of that, we have to familiarize ourselves with something like an Hadamard operation, which we haven't probably heard before if you not have started working on quantum computing. So this is a challenge as well. And then, of course, in the domain, we have lots of physical constraints. Many abstractions simply don't work. In the conventional realm, in the meantime, we can perfectly work with programming languages, maybe with gate net lists and stuff like that, which abstract away, you know, energy consumption, electricity. So we can completely ignore, to some extent, electrical engineering, although everything we do in conventional computing is based on electronic circuits. We can ignore all that and still can realize applications, software tools. In quantum computing, you still have always to be aware that there are lots of physical constraints which we simply cannot ignore. Error correction is a huge topic and many, many other aspects as well. So there are a couple of challenges we have to change and we have to cooperate. And this is one of the reasons why we not simply can reuse, we can get ourselves inspired by conventional design methods, but we cannot simply reuse them. And last but not least, a huge problem also is the entire complexity of everything. And to make that point, let me quickly give you an example of a design task for what we need software. Simulation is logic simulation is one of the simplest design tasks in the conventional realm. If I give you a circuit and I give you an input assignment such as this one here, you can very easily do logic simulation with that, because you know this is an inverter here, and if an inverter gets a 0 as input, you know you get a 1 as an output. The same with this inverter here. And then if you know this is an AND gate, it gets a 1 as an input, and another 1 as an input, you know the output is 1 as well. So a logic simulation is actually very, very easy. It's linear in the number of gates of a circuit. So this is a very simple design task for which we can have very efficient methods. If you now want to do exactly the same for quantum computing, we have a problem because, as said, we can have single assignments, like this signal can be 0 and 1, but it also can be 0 and 1 at the same time. And this usually is represented in terms of so-called amplitudes, so those alpha variables. That means if you have a quantum state, you need to describe kind of the portion of how this quantum state is with respect to the respective basis states. So for two inputs, for two input signals, a quantum state can be in 4 possible states, and it can be in all those 4 possible states at the same time. And you describe that by having 4 dedicated complex values, these alpha values here. And I don't want to dive too much into the details. The bottom line is simply that just for the simulation, a single state need to be described in this fashion. And the message here is simply that in order to describe such a single state, you already require an exponentially large vector, because you have to describe kind of the portion this qubit state, this quantum state, can be in for all possible basis states. That means for 2 inputs, you need a vector with 4 elements. For 3 inputs, you need one with 8. So already just representing the input state causes an exponential complexity you have to deal with. And as a consequence of that, tasks which have been simple in the conventional realm suddenly render exponentially complex in the quantum computing realm. And this is another big challenge we have to deal with. On top of that, we have to deal with things like interdisciplinarity. We have to work a lot with physicists in order to understand that we solve the right problems for and develop the correct methods. There's still a huge mess when it comes to terminologies and formalizations. We have the same words for completely different aspects. So it's a very challenging domain, but it's also very inspiring and it's fun because there's lots of things, lots of development you can do. So long story short, this slide is supposed to showcase a little bit the challenges we have in order to deal with these problems. And this is what I want to make a case for. So in order to address these challenges, we need more computer scientists or engineers, which in addition to the physicists, help us overcoming this challenge. And this is literally what we do in our research group, but we also have an entire community about it. We're trying to develop automatic methods and software tools for the design of quantum algorithms, quantum circuits, quantum systems. And this is sort of like we're doing that by, on the one hand side, developing the basis of it, core methods and core data structures. And once we have those, based on that, we're developing compilation or synthesis methods, which from their design task is very similar to conventional compilation or conventional synthesis, but now just with these different operations. But you still try to compile or synthesize something from a high-level representation to a low-level representation. We develop simulation and verification tools. As I sketched before, simulation is an important topic. How to deal with the complexity, this is one of the things we have to do. And then, of course, there are a couple of developments towards how can we assist the end users, the end user who wants to run, for example, or who wants to solve, for example, his optimization problem, his logistic problem, his, I don't know, climate catastrophe simulation with a quantum computer. How can we assist those in order to develop quantum algorithms for those applications without the need to make them a quantum physicist, as an example? And this is what we're working on in order to deal with the challenges I mentioned before. And now I would like to just give you an idea and a sketch of some possible solutions in this direction, and also want to make the point that although I sketched that everything gets more complex and everything is challenging, now I also want to make the point that in order to get used to that, in order to get an understanding and in order to contribute to that, there is actually not a huge entry barrier. So I'm trying, in the next 5 minutes, I'm trying to make the point that everyone you in the room can actually contribute to that, because you don't have to become a quantum physicist in order to make a difference here. You just have to utilize the expertise for this domain. And to make that point, indeed, quantum computing, although it sounds complex and it sounds like you have to have a quantum physicist education in order to understand that, many of the things, many of the problems and the challenges I sketched can be boiled down to very clear abstractions we very nicely can work with. As an example, I already mentioned that a quantum state can be represented in terms of a vector, which is described by these complex numbers. And at the same time, a quantum operation, such as the aforementioned Hadamard operation or Toffoli operation, they can be represented in terms of an operation. And even though you might not be familiar so much, or you have a hard time getting an intuition, what is a Hadamard operation? At the end of the day, everything can be boiled down to a matrix. And this is great because just with those representations, a matrix for operations and the vector for states, you can already develop and you can work on developing dedicated design solutions or software tools for certain important tasks. As an example, I mentioned quantum circuit simulation beforehand. So what does it mean? I give you a quantum algorithm or a quantum circuit, namely a quantum functionality and an input state, which is supposed to be applied to this algorithm or circuit. And then the task is, okay, what is the output state of that? And this is actually very conceptually very simple task, because if you give me a quantum functionality, an operation in terms of a circuit, an algorithm, and an input state, all you have to do is you have to multiply these two guys together. So you have to do matrix vector multiplication in order to get your output state. And by doing that, if you implemented something like that, you developed a quantum circuit simulator. It is as easy as that. So the entry barrier indeed is just, even if you have no clue about the meaning and the semantics of the operation and of the input state, if you are able to develop a very efficient matrix vector multiplication, you contributed to a quantum circuit simulation, which is one of the biggest and hardest problems in the domain. Same thing, I mentioned compilation and synthesis. What this is about, it's actually about, okay, how can I realize a sequence of operations, of elementary operations, for example, which when multiplied together realizes my desired quantum functionality, my desired operation. So every gate is an operation, so every gate is a matrix. And if you have a sequence of gates, you simply multiply these gates together, and then the task becomes, okay, what sequence of these matrices or gates respectively form my desired overall matrix. So also here, even if you don't have a good understanding or an intuition about Hadamard gates, Toffoli gates, if you can sort of decompose an overall matrix into a sequence of matrices, ideally of elementary matrices, elementary operations, you solved a compilation problem for quantum computing. And then you have things like, okay, we have entire compilation flows where we, for example, try to optimize afterwards. Like we know that, for example, these two H operations here, they cancel each other out. We know that a sequence of those gates here, it can be reduced to a cheaper sequence of gates. So you have lots of combinatorial problems where you may want to apply rewriting rules or optimization techniques, and where you just have to work on a different rule set, but eventually still will be able to make a contribution, and you don't have to be a quantum physicist for that. And then last but not least, and with this one, you solve compilation, or you may contribute to compilation to synthesis. And last but not least, also verification. So what is the deal here? You now got a high-level operation, like on the top here, and you compiled it down to a low-level operation. And now you want to know, are they still functionally equivalent? And also, this is something you can actually work with, because what you have to do is you have to take this circuit here on the bottom, you have to derive the corresponding matrix representing this functionality, and then you can compare those matrices with each other. So what I'm trying to do here is I'm trying to make the point that although we have lots of challenges in quantum computing, and we are doing research how to develop them, the basis of many of the design tasks are literally vectors and matrices, which can be represented by 1- or 2-dimensional arrays. So a straightforward, a simplistic solution for that is simple. You just take the matrices and the vectors, and for example, you multiply them together. So the entry barrier is actually not that high. The question is just sort of how to deal with the fact that all those matrices and all those vectors are exponentially complex. And I hope with this, on the one hand side, we're able to make the point that everything is challenging and complex, but in order to make a difference, the entry point is easy. And for some toy examples, you can very quickly get involved. And then you can think about, okay, how can I tackle the respective complexity? How can I find a better quantum circuit simulator, a better compilation method, and so on and so forth. And for this, of course, we have a couple of developments going on in the community. We have dedicated data structures such as decision diagrams, tensor networks, ZX calculus. And in the final, let's say, 5 minutes of my talk, I want to just, again, sketch one of those alternatives and illustrate a little bit what is the main idea of things you can do in an effort to give you another intuition. How can we tackle these kind of problems? And for this, just let me quickly recap a little bit the main idea of a dedicated data structure, which is used in order to represent matrices like this one here. And this data structure is a decision diagram. It's very popular in the conventional realm. It has been heavily used for the conventional design of circuits and systems. And it can be used for representing quantum functionality, or quantum operations, or quantum states as well. And what is the idea here is you take your overall matrix and then you try to decompose it into 4 submatrices, which you represent in terms of a node like that with 4 successors, every successor being pointing to one of those submatrices. Because if you do that, then you can identify, look, these 2 submatrices are equivalent, they are identical. And that means you don't have to store them separately in your memory. You can actually share them. And then you simply have 2 pointers pointing to the same matrix, saving you 25% of your memory. Then what you can do is you can see all those entries in the submatrix. They are identical or almost identical. They only differ in one subfactor, namely 1/2. So what you could do is you could multiply out this common subfactor and add that to the edge weights. And then you have a semantic, like when you follow one of those edges and this edge has an edge weight, you simply multiply this factor with all the entries of the matrix this pointer is pointing to, and then you still get your original matrix entries. And this doesn't help a lot for this matrix, but if you look in this submatrix here, you can see also here you have a common subfactor, namely -1. If I multiply that out, so it's happening right now. So if I multiply the -1 out, I get this submatrix. And now I see that suddenly this submatrix is identical to this submatrix. So I can merge these two submatrices as well, because they are identical. They only differ by this common subfactor here. And that means if I follow this pointer, I just take the original matrix. If I follow this pointer, I just take the matrix and multiply all the entries with -1. And by this, I can save another 25% of my memory, just with this small trick here. And with this overall, I can reduce the memory consumption by half for this particular example. And I hope this transported a little bit the idea. I can now do this in a similar fashion, in a recursive fashion, for all the resulting submatrices as well. So I can decompose those submatrices as well. Then I can use some sharing here as well. And overall, if I do this recursively to all those levels, I ending up with a representation like that, which represents the same thing as my exponentially large matrix. With this decision diagram, I can also do, I don't dive too much into details, but believe me when I'm saying I can do matrix multiplication with that. I can do matrix vector multiplication. So I can use this in a very similar fashion as I can use matrices and vectors. But ideally, this is giving me a much more compact representation. And I'm not saying this is solving all the problems. In the worst case, also this is exponential. If decision diagrams would always be polynomial, for example, or even linear for every arbitrary quantum operations, then I guess I wouldn't need a quantum computer. So also here I am reaching my limits, but I hopefully reach these limits later than compared to using matrices and vectors. And this is kind of an idea what I wanted to sketch. And overall, this is kind of what we're doing and what the design automation community is trying to accomplish right now. We're having these challenges and the problems are getting harder, but we're trying to utilize the decades of design automation expertise, like the data structures I mentioned before, but also other things. We're utilizing reasoning engines, SAT solvers, for example, in order to make a difference in these kind of domains. And then we are trying to incorporate all that into tools for quantum computing, tools which can be used for representing matrices and vectors in efficient fashion, which can be used for simulation, for compilation or synthesis, for verification. So we have developed a huge amount of tools, we, the design automation community, but also we as a group in Munich. And if you're interested in that, all those tools are publicly available in our GitHub, where you can simply clone the corresponding repositories and then play around with that. If you don't want to, deal with codes, what we also have, we have a web-based tool. When you simply go onto this web page here, you can directly access a web interface where you can just load in quantum algorithms, and then you can simulate those algorithms operation by operation. And at the same time, you see on this other box here how the respective decision diagram representation of the quantum states evolves. This tool is not as powerful as our GitHub implementations, but it gives you a quick entry point. If you just want to play around, you just open the web page and then you click around a little bit, and then you can get an intuition how, for example, the data structure behaves. All of that can also be used as pure black box. That's what we do with our end users. For example, if we have an end user who just wants to run his or her, let's say, a logistic problem, then he or she can simply write the corresponding algorithm, put it into a simulator, and he or she doesn't have to know anything about decision diagrams or reasoning engines. He or she can simply use our tools and in order to simulate his or her circuit. So also this is something which can be done. And of course, further information is available on our webpage. With this, my time is more or less up. I hope I was able to convey a couple of main messages. First, after decades of physicists building quantum computers and driving the topic forward, now is really the time to get more computer scientists or engineers involved in this topic. Second, this requires to tackle certain challenges, which I sketched at the beginning of my talk, which are challenging, but it's a very interesting field, lots of interesting and exciting problems to solve with. And I hope I was able to convey the message that in order to make a contribution here, you don't have to become a quantum physicist. There are descriptions like these matrices and vectors, and also problems like decomposing a matrix into elementary operations. There are a lot of things where you have to have a rough basic understanding, but certainly no years of expertise in quantum physics. And this is what I strongly believe, there are a couple of problems where, with particularly a different background, a background different than quantum computing, we can make a difference because, as I sketched with the decision diagrams, we develop them and we are not sort of like, we are totally smart that we developed them. We just reuse them because they have been used very heavily in the conventional realm, and we just redeveloped them for quantum computing. And with this, we made this kind of contribution. I think that's what quantum computing really needs: more expertise, more from the conventional, from the tools and methods which have been developed over decades in our respective communities. We should introduce that into quantum computing because I sincerely believe they make a huge difference there. Because there are lots of the problems we are facing in quantum computing, in the development of algorithms for quantum computing, are typical informatics, computer science problems, combinatorial problems, typical problems for which we actually have solutions which have been developed over the past decades. And with this, I hope I was able to convey some ideas, convey these messages. Thanks again for having me. Sorry that I cannot be there physically, but I hope I was able to give you a couple of ideas and encourage you to get involved here. Thank you very much.
Thank you so much, Robert. This was fascinating, interesting, and exactly, I think you hit exactly the right abstraction level for what we needed in this audience. It's really nice to talk about quantum without explaining exactly what the qubits are. And for those who are now very curious about this, there is a workshop in the next session where we'll go much deeper into some of these things and understanding some of the things. But any questions to Robert? Kim. And Robert, you will say if you can hear.
Yep.
If you cannot see, I don't know. Okay, thank you very much for a nice presentation. I like all these decision diagrams. So I'm a model checking person. I model check also circuits, conventional circuits, using BDDs that look pretty much like this. I was thinking of probabilities when I looked at your matrices. Maybe this is a wrong statement, but would it be fair to say that the kind of symbolic methods, decision diagrams that have been successfully used to analyze conventional circuits, if you have that background, I mean, it seems to me that then we should dive into this and extend these tools to these exponentially in many steps. I mean, I just want your confirmation of that before we engage in this activity.
Yeah, so I hope I got the question.
Do you know about the model checking community? That, by the way.
So yeah, I think I got the question. I completely agree. So indeed, let the model checking community, let the BDD experts, let they really getting involved with quantum computing, because I think there's much to learn, and that's what we did as well. We knew that in the conventional realm, decision diagrams have been heavily used. And it's not just that they had used one type of decision diagrams. We know, for example, with Shannon decomposition, it's great for something like additions or symmetric functions, but it completely tanks for something like multiplications. And then you had different types of decision diagrams for different classes of functionality. And then you know that, for example, multiplication is probably better with KFDDs and something like that. And for quantum computing, we are really at the beginning. We have kind of this type of decision diagrams. There are a couple of other types which literally are subclasses of this type of decision diagrams. What we don't have right now is maybe we need a different decomposition method for different class of quantum functionalities. We hardly have theoretical results like bounds in the conventional realm for everything. You know, the upper bounds, the lower bounds of decision diagrams for this particular classes of functions. So long story short, I think indeed whoever is working on decision diagrams for conventional circuits and systems, they find a great playground in quantum computing, because classes, theoretical upper, lower bounds, different decomposition methods, there's a huge spectrum of topics you can research here. I hope this was the question.
It was a good answer.
Very good. Any other questions? Yes, over there.
Thank you for your talk. So you seem to imply that it's a long time in the future that factoring might be possible. Can you hear me?
Yeah, if you can speak up a little bit louder, that would help.
Okay, so you said it's a long time in the future that factoring might be possible. Is this because the physicists haven't been able to figure out how to implement the operations in Shor's algorithm, for example?
I'm really sorry. Maybe Jan, can you quickly repeat close to the mic?
So the question is, you mentioned that factoring would be in the future.
Yep.
And why is this the reason? Is it because the physicists haven't really solved the let's say the physical aspects of it?
Absolutely, I got it. So the factorization algorithm is around since the 90s of last century. So theoretically, we know that there's a theoretical solution. Right now, the problem is scalability and also fidelity a little bit. So we have no problems. We have physical quantum computers which can factor 15. So I'm not sure if this comes to a surprise to you, but the factors of 15s are 5 and 3, just in case you haven't noticed that. So this week, what we can solve with quantum computers, but to really break cryptography, we really need much bigger bit widths. And for this, we simply don't have the scalability and the stability yet. And I'm not really an expert there, but the experts telling us this is probably more like the long-term application. So IBM, Google, and so they're not investing a lot right now because of cryptography, but because of optimization problems. But there might be a decent chance that maybe in 10 years, maybe 15 years, maybe more, also factorization might be an issue, which is why post-quantum cryptography is an issue, just not in the short term, more in the long term.
Is it more the number of bits or the types of operations that you have to get rather specific operations, values, and
no, you don't need rather specific operation. You can actually already boil it down to the elementary operations. We can compile it down to the elementary operations we already have. All the quantum computers and the elementary operations they support today, they are universal. You can realize any quantum functionality with it. Really just scalability in the number of qubits, but also fidelity in the way how stable are those qubits. This is the issue. But theoretically, conceptually, it's solved. That's no problem. It's more like getting it done on the physical machines in the scalability, in the scalable and in the stable way we need it.
Thank you.
Yeah, so it's both in the number of bits, but it's also in the depth of the logic you can do with these gates. And the limit of that is because of the noise, it cannot sustain the quantum state.
Exactly.
Yes, one more here.
So thank you so much for your presentation, and I really like that you state that we need also to start looking beyond just the hardware creation, but also on other topics. And actually, this is something that I would like to know maybe your perspective on this, because today we are speaking a lot about how to develop a quantum computing, how to use a quantum computing. However, on the practitioner side, they are having very different conversations on how they can transform the world and how everything will change with the quantum computer. So what do you think as researchers, or how should we maybe address also our conversations with the practitioner side so we can maybe help avoid the vague ideas that might happen and also all the hype around the quantum computer? How do we connect with the human part of quantum computing? That's a bit of my question.
It's a very broad question. Maybe I see two developments here. First, from an end user perspective, it's really the question like, what is a quantum computer? It is certainly not the computer which replaces existing computing. It is an accelerator. It is more like, I think the whole computing direction is going more and more heterogeneous. So in the past decades, we had CPUs and GPUs, and that's literally it. In the meantime, we now got AI processors, we got dedicated processing machines. And I think the quantum computer, or as you also can call it, the QPU, is just yet another thing. So I really believe that in the future, we're going to have problems And the task is to decompose these problems into sub-problems and then to find the right computing machine to solve that. And one sub-problem might be solved with a traditional CPU, another with a graphical processing unit, and then yet another sub-problem with a quantum computer. So from an application point of view, I think that's how we should see quantum computer. They are not this wonder machine, they solve everything, but for some problems, they are the best way to go if they are scalable and if they're stable. So I think this is one way of seeing that as just one tool out of many. And the other thing is, of course, how do we get the end users attracted to that? And that's a big challenge because quantum computing is conceptually and from the paradigm so much different. We have to really think about what we need. And I think also here, we of course need quantum computing experts, but we also need people with a computer science background who are familiar with quantum computing. But also here, not everyone needs to be an expert on quantum computing. The end users, in the ideal world, the end users get shielded as much as possible from all this confusing quantum computing stuff. In a similar way, like how everyone can today write a dating app or any kind of software without really having a deep understanding about computer science or computing. It's a long run, but I think eventually we need to get there. That's sort of like you know what we can use quantum computers for, and we're making them applicable and usable without having the need that everyone needs to become a quantum expert. It's a long run, and at the moment we have a lot of development and we need a couple of experts for quantum computing, but the goal should be that eventually everyone should use that in the same fashion everyone uses computer today.
Thank you.
Yeah. Thank you for your inspiring and great talk. I have a question on the big players that you mentioned at the beginning. You mentioned, I think, Microsoft and Google and maybe Amazon. So I assume they also work on probability of quantum computers. I can't imagine these companies do something else. But is it known what is their strategy? Is this public knowledge, or do you say a little bit what their approach would be?
I mean, of course, I cannot speak for them. Don't know what their long-term vision is. And definitely, I think they kind of identified a couple of years back that quantum computers are getting real, and they of course want to kind of lead these kind of developments and position themselves. And for the hardware vendors like Amazon, IBM, and so on and so forth, they just want to sort of want to have a lead in the provision of the computing technologies. What I find much more interesting are the end users. And here good examples are, for example, in Germany, Volkswagen or BMW. So what they want with quantum computing. And here also Infineon, by the way. And here my take is they're currently getting also this feeling like quantum computing is getting momentum, and they don't want to get left out. So what they're doing, they use their financial resources in order to create research groups which play around with that, with quantum computing. And right now they're playing around with toy examples. So they don't optimize their production right now using quantum computers, but they kind of derive toy examples so that they get acquainted, that they familiarize themselves, so that if in 5 years really quantum computers reach a level so that they can, for example, optimize their productions or their logistics or whatever, they have already expertise. So right now it is more like a bet that, okay, in the next years, maybe this thing gets really serious, and then the end users, but also the hardware providers want to sort of have the expertise, want to be prepared. And I'm saying it's a bet because I'm personally, of course, I'm really optimistic that this is going somewhere. But the same with AI, maybe it takes a couple of hype loops. Maybe we're entering a quantum winter and we need another 10 years or so. Similar with AI, it took them decades until AI became what it is today. And with quantum computing, nobody really knows. There might be a decent chance that indeed in 5 years we have them and we can solve practical problems with that. It could also mean that in 5 years, we're going to have another down, and it takes 10 years. So right now, what these companies are doing, IBM and so on and so forth, they want to establish a lead in the technology, in the provision of the hardware, and end users like Volkswagen, BMW, they trying to check out whether or not this is something they can optimize their processes with. And I would say this is, I mean, that's my interpretation. Of course, I am not in these strategy meetings of these companies, but that's what their development looks like to me.
Yeah, thank you very much for the interesting talk. I had a class when I was a student 20 years ago, and at that time I was told that people could actually factor number 6. And yeah, today you say it's 15. I think a week ago I have been to a conference, actually heard that 21 was possible as well. And I'm a little bit thinking like, shall we invest that much effort right now? Is it the right moment to prepare? I mean, all this machinery for something that maybe before we retire, we might not even have the hardware to execute our algorithms on. So I think a little bit like risk assessment. Shall we invest lots of effort right now? Or could we as well just wait 5-10 years until we see that actually these machines are probably going to happen? So what's your take on this?
Yeah, good question. And to be honest, I don't think you want to have an answer for me because I might be biased. And to be honest, I'm also, to be really frank, I have no idea whether or not the physicists will accomplish the scalability we need and so on and so forth. My take why I'm doing it, and I started with that 10, 15 years ago, where it was even not the momentum. So 10, 15 years ago, there was no momentum on quantum computing. There was no no shine doing it. I'm doing it because I think they're offering interesting problems. So from a research perspective, that's just interesting. And also kind of my motivation is a little bit that in the conventional realm, I'm still heavily involved in design and developing design methods for conventional circuits and systems. And the frequent problem we experience there is the so-called design gap and verification gap. You probably have heard about that. Means the semiconductor industry was always more powerful in developing, always in advance in developing more powerful and complex circuits and systems, and the design community always had to catch up with this development, and we never really were able to utilize that. In quantum computing, I would say that right now we probably have more powerful tools than physical capabilities, but if this technology is really breaking through, I'm pretty sure we're reaching a design gap as well. And this is my take a little bit. Whether or not you should invest, I leave that to you. That's everyone's personal decision. I think it makes sense to develop these kind of tools because we are most likely, there's a decent chance that we most likely run into similar design gaps or verification gaps as we have in the semiconductor industry. And when quantum computing is really getting their breakthroughs, I'm pretty sure the complexity will be overwhelming. And if you're not starting developing corresponding design tools now, we're going to have serious problems once these technology really make it. But again, this is just my take. I might be very much biased here. So don't make your investment decisions based on my take here.
Thank you, Robert. I would like just if you could quickly comment on a question. So when we see and listen to you, it's quite clear that what is called programming, I would consider being logic design, whether it's some strange logic gates, as you're saying, and of course anything we program we could actually build like that in a software tool, but we would rather not. So how do you see the true software, I mean a higher level extension into this? Would that be to map onto to the gates, or do you see anyone looking into to that? So because the trick here is, as you also say, is that the way we have to think about the implementation here is so different that it will take a long time for us to adapt to this. Can we, let's say, mitigate that and use our normal way of thinking and then having tools to actually transform that into to the gate?
Very good question. And my take here, or my answer would be, we not only should do that, actually, I think we don't have an alternative, because I don't see any way that in the next years or so, we're getting this quantum workforce, that's usually how it's called, or these many people with the corresponding expertise. So we won't have enough people actually to have this expertise in quantum computing to make it work. So I really see what we should utilize, and we should utilize as much as possible from the conventional computing paradigms, and we should shield as much as possible people from quantum computing. At some point, we need people with corresponding expertise, but there are a couple of things where we can shield them. And maybe, I don't know, for those of you, there was someone in the audience who's on model checking. Sometimes you can compare it with that very similar. Like we have a combinatorial problem, and you formulate that, for example, in terms of a SAT instance or in terms of a decision diagram or something like that. And also here, we often shield the end users from the precise SAT instance or from the precise decision diagram structures. So this is possible. So we can develop tools so that the end user still can formulate their problem in conventional fashion, and then a tool automatically or semi-automatically where we need a little bit more people with quantum expertise, but lots of this stuff can be handled. So I think that's possible, and I think it's the only way where we can get this off the ground, because we won't have that many quantum experts as we actually would need otherwise. Hope that makes sense.
That makes perfect sense. Thank you very much, Robert. Let's give Robert a hand.
Perfect. Thank you very much.